I'd like to thank you for joining us. This is our monthly lecture series that's sponsored by the Alaska Center for Energy and Power and Cooperative Extension at the University of Alaska, Fairbanks. Tonight we're going to be speaking about biomass and whether it's a sustainable option for Alaska. And obviously here in the interior we have pretty significant biomass resources, and so that's a topic of interest. There's a lot of very interesting projects going on in the interior, and we're going to learn a little bit more about at least one of those this evening, and also what's being done at Cold Climate Housing Research Center in terms of looking at wood burning and emissions and clean wood burning technologies for home heating systems. I'd like to just take care of a few housekeeping items. First of all, I'd like to ask you to turn off your cell phones before we get started. We're going to hold questions and answers till the end of the presentations to make sure that our presenters get enough time to get their presentations out of the way. We've been holding the lecture series here at the Blue Loon for several months now, and one thing that we're really interested in getting is some feedback from you. We've had an online survey that a number of people have already completed. Since you're here at the Blue Loon, you obviously don't think that this is a terrible venue to hold these lecture series, but we'd like to get feedback. We've held them at the library downtown, a number of different locations, and we'd really like to hear what you think the best location is, what kind of topics you'd like to hear. And so there's a survey on the back table that you could fill out this evening. There's also additional material both from our presenters this evening, as well as from the Alaska Center for Energy and Power and some of the projects that we've got going. And also, there's an email list if you want to sign up for that, not just for information on future lecture series, but other things that are going on that are energy-related, different topics or conferences or publications that are out there. So anyhow, that's an opportunity for that. We try not to bombard people with too much information, but when we think there's something important that people are interested in, that is a way for us to get that out to you. So that sign-up sheet is in the back there. This evening we've got, I'd really like to thank our speakers. I've sort of been, I'd say, elected to pinch hit for this first presentation to talk a little bit about the background of biomass, what biomass is, putting it into context a little bit. And then we have speakers this evening from Chena Power, Michael Gomes and Jesse Warwick, and then John Davies from the Cold Climate Housing Research Center, and I'll introduce them with a little bit more detail later, but I'd like to thank them for joining us this evening. So am I forgetting anything? Marcus, I haven't given an introduction here previously, so okay, we're doing all right. Okay, I'm going to go ahead and just go right into a little bit of background on what biomass is and what we're going to be speaking about tonight. And essentially when you go to the dictionary definition and you look at what biomass is, it's organic materials, wood, municipal waste, agricultural crops that you can use as a fuel source for energy, and that's really what we're talking about here. So it can either be burned directly or processed into biofuels such as ethanol or methane. We're not talking about that here. There is work being done at the university related to that through the School of Natural Resources and Agricultural Sciences. They're also involved in other work such as looking at the concept of short rotation woody biomass crops, which is something that's being done in other places in the world. And that work's being led by Steve Sparrow, who's actually here this evening. Steve, can you raise your hand? I can't see him, but he's over there. Okay, great. Well, he's a great resource that we have here locally, and unfortunately, because this is such a broad topic, we couldn't bring everyone in to speak. We almost thought about having a phase 1 and a phase 2 for this. Today we're talking a little bit about combustion technologies, about how you might use biomass for either heating your home or generating electricity. There's a whole nother side to this question, which is where are you going to get that biomass from? Is that from growing a short rotation crop, like Steve's been looking at? Is that from harvesting maybe fire breaks? There's all kinds of different options for sustainable harvesting of biomass for energy projects. And so there's a lot of people involved in that. We've thought about having a separate lecture series on that topic. Let us know if that's something that you're interested in hearing about. It's interesting, too, to note that Fairbanks was actually electrified by biomass back well into the 1920s. I don't know if any of you have seen the historic photos of the downtown Fairbanks power plant, but it's a pretty striking image that I wish I had thrown in this presentation that shows a fairly non-sustainable use of biomass in the interior. So essentially, though, we are going a little bit full circle in that now we're talking about increasing our use of biomass, but that's really how Fairbanks was developed, using our biomass resources here in the interior for power generation, for heating, and things like that. And I think now we're coming around full circle to looking at using those resources a little bit more prudently and more sustainably, and looking at cleaner burning technologies and things like that. When we look at biomass, and I brought in a couple logs here. Actually, I had somebody steal some logs from their neighbor's woodpile earlier today. But this is a nice birch log that somebody is planning on burning this winter to heat their home with. And one thing that's really interesting when I speak to school children around the state is they really don't understand where this wood comes from. Where does this mass come from? And when you ask them, a lot of times they'll say, oh, it comes from the soil. That's a really common answer, is that the tree is pulling up nutrients from the soil, and that's what's actually creating this wood mass. And that's partially true in that that's where the water content is largely coming from. But the truth is that this is really stored solar energy in this log. We're storing solar energy, and what we're doing is we're taking carbon dioxide from the air, we're sequestering it in this piece of firewood or this tree when it was growing, and we're combining that with water and creating glucose and various kinds of carbohydrates, and then oxygen is produced as a byproduct of that process. And so what's interesting is that this is basically mostly carbon dioxide that's been sequestered from our atmosphere. And then when we go ahead and burn this log, it's going to release that carbon that was sequestered during the lifetime of this tree. So when we consider whether this is renewable energy, it really has to do with whether you're replanting that tree or whether that land is now being paved over for parking lots or something like that. Then maybe it isn't sustainable, maybe it's not considered renewable, but in general it's assumed that you're replacing the biomass that you're cutting down for whatever kinds of energy use that you intend to make of it. So in the lower 48, biomass is actually used quite a bit for power generation. Mostly industrial uses, about 80 to 90% is really for industrial technologies. What's generally done is that biomass is combusted. It's used to generate steam and then drives a steam turbine. And so it's a fairly robust, not a very new technology, and it's been done on a large scale in many places and is being done in the lower 48 in many places. Here in Alaska, there was until a decade or so ago, there was 2 large-scale mills in southeast that were using biomass energy for electric generation for on-site use, for example. In the U.S., about 1% of total U.S. generating capacity is from biomass, which is primarily waste products from various wood processing facilities, sawmills, things like that. And as a whole, biomass accounts for about 4% of total energy use in the U.S., and the reason why that's quite a bit higher than the 1% for power generation is because of ethanol and fuel production from biomass. That's become a bigger component of our overall energy use in the state. Worldwide, obviously, biomass has been used for millions of years for heating and cooking, and so today it's still the primary energy source for half of the world's population, not necessarily for electricity, but for heating, for cooking. Europe is currently the leader in clean conversion technologies, so using biomass for heating or for power generation with reduced emissions. And again, when you're talking about clean biomass, you're still combusting the wood, and so you're still getting carbon dioxide. It's just a question of what other kinds of byproducts or particulates and how you can reduce those types of emissions is really what the goal is. Advantages of biomass, it can supply on-demand baseload power, heating. Obviously, it's available when we need it, unlike maybe wind power or solar energy. We know that it's available as long as we have enough wood in our wood pile or enough wood chips or municipal waste to run our systems. It's available year-round with storage. carbon neutral. We talked about that a little bit. It can be processed into a syngas or a liquid fuel for storage, and it can be used for power generation, space heating, or transportation applications, which is nice as well. Disadvantages are it's expensive to handle because it's got a low energy density. There's the number of BTUs in this log is significantly less than a comparably sized gallon of gasoline. So that means it's got to be used near its source because it's just not economic to transport it long distances. It's labor intensive, which can be a good and bad thing. What that means is that there is the potential for more local jobs creation and things like that because the money that you're going to spend to harvest biomass and to use that in a system is probably going to be expended locally, close to the source, close to where the fuel is available, and that means that you are supporting local economic development often with these types of systems. Smaller scale technologies for power generation are still emerging. It's challenging at the smaller level to generate power from biomass. We're going to hear about one of those systems that is in development this evening with China Power. And small-scale production of liquid fuels is similarly expensive. This is typical to a lot of the technologies that we've been studying at the university, and the fact is that you often can do these things technically. Technically, it's not impossible to do a lot of these types of things. It's a question of how much money do you want to spend on it, and so what are really your goals? Are you looking for an economically viable way to produce liquid fuels from biomass at the small scale, or do you just want to do it at any cost? You know, there's different questions there, and if you don't have liquid fuels, for example, available from other sources, you might be willing to spend a lot more money to get a liquid fuel from biomass versus what we have available today. So the economics are actually really critical when you look at biomass. There's two things we talk about when we talk about biomass. We talk about combustion. That's the way we've been doing it for millions of years. We basically burn it in a fire. It's a robust process. It's really easy to maintain. You can use boilers, convert heat to hot water or other medium and generate steam for distribution and then you could use that for power generation too. There's thermodynamic limits on the efficiency of combustion process, and then inefficient systems, which I think John's going to talk about a little bit, do create more air pollution and do require more fuel to operate. So efficiency for biomass is an important consideration because there is a cost for the fuel, and you want to make sure that the system that you're running is as efficient as possible so that you are so it's as economic for the user as it can be. Gasification involves the partial combustion in a low oxygen environment to create a gas, a syngas it's called. You've probably heard that terminology from other places. So it's carbon monoxide, hydrogen, methane, CO2, nitrogen. That's what you wind up getting. It's got a low energy density compared to like a natural gas or something like that. So again, it's got to be used close to the source. It's got the potential for higher energy conversion efficiencies in combustion simply because you have higher temperatures involved. But it's a more complex process. It requires a very uniform biomass fuel, and so you need to do usually some pre-processing of the fuel for a gasification process. This is just a little bit of a comparison between the two of them. You know, gasification can be more efficient than direct combustion, but often at small scale, there's challenges involved, especially in the economics, integration with other processes and things like that. So in the interior, there's a lot of different projects going on. I'd really hope that Devany Plentovich, the biomass program manager for the Alaska Energy Authority, could come and talk to us a little bit about that. In Tok right now, Alaska Power and Telephone and NextEra are working on a biomass combined heat and power system with the State Division of Forestry supplying the wood for that project. Tanana has two garn boilers in their washateria that have been online since 2007, and they just received a $1.8 million grant from Department of Energy that's going to significantly expand what they're doing in that community in terms of biomass. Galena has been working on a proposal that, and their project isn't funded, also looking at a project similar to what Tok has going on. Delta Junction has been doing some wood for space heating applications, and Fort Yukon also has a project that's underway. Superior Pellets here in the interior would be the first, will be the first commercial pellet manufacturing facility in Alaska. This is a picture of that from the Fairbanks Daily News Miner. So the interior's really taken a lead in the area of biomass energy projects. There's still some research challenges out there. The Alaska Center for Energy and Power is a applied research program, so we're always interested in that. Reducing capital costs is a major constant issue with a lot of these types of technologies, so trying to get those capital costs down, improving efficiency of systems. Just inherently, the smaller the system, the less efficient it is, lowering emissions, and then improving integration with other existing generation systems. Those are some of the areas that we've been working on in terms of, from an engineering perspective, in terms of research in biomass. So, and that is all I've got for my presentation. I would like to introduce, John, are you going to be our first speaker? I hadn't spoken with you guys about that. Where is John? There you are. How about is that all right if I bring you up first? Is that all right? John Davies has 4 decades in Alaska, and he's worn many hats in that time period. He currently is the senior policy researcher for energy. I think I put those words, I think I mixed them up a little bit, at Cold Climate Housing Research Center, and he's going to speak about residential wood burning issues and solutions. What does that mean? Thank you.
Good evening. Can you hear me okay? Okay. So this is the correct sequence of words, Gwen, right here. So I'm going to talk about residential systems, and that basically means wood stoves and that sort of thing, and some of the issues that are related, mostly the PM 2.5 emissions issue. Gwen touched a little bit on the question of whether wood burning is carbon neutral, and I'm not going to talk too much about that. A lot of people assume that it is, and it really depends on a lot of things, but fundamentally it depends upon whether your source is sustainably grown. So in the forests around Fairbanks generally are, if you're on public land. So if you're cutting down firewood from the state forest, for example, that's a sustainable source. If you're, like Gwen said, if you're burning wood that's from a clear cut for a parking lot or something, then maybe it's not so much. But I'm not going to, that's a very controversial topic, depends on time scales and lots of things, so I'm not going to get into that. I'm going to talk more about the issue of particulate emissions for wood burning, and since it's a hot issue for Fairbanks because of the PM 2.5 issue, the non-attainment issue, so I'm going to start off by saying, okay, what is PM 2.5? So PM 2.5 in general are aerosols that have a aerodynamic diameter of 2.5 microns or less. And when you say PM 2.5, you mean everything that's that size and smaller. PM 10 is everything 10 microns and smaller, includes 2.5. So in the case of wood smoke, we're talking about products of combustion from burning wood, and in particular we're concerned about 2.5 because that's the size that has been most identified with health issues. So there are a number of pathways into the body. You can breathe it, inhale it. The larger particles generally stay in the nasal area, and the very small particles get down into the alveoli deep in your lungs. Here's a kind of a distribution of sizes and where they end up. The line here that's along the bottom are the diameters. So there's this 5 microns. PM 2.5 is about here. You see there's kind of a peak right here in this red line, and the red line is the deposition in the pulmonary system. And so you can see that there's a significant amount at 2.5 and smaller that gets deposited in, deep into your lungs, and that's the piece that we're concerned about from a health point of view. The short-term health effects as summarized by EPA is this list. I won't read it all, but I've bolded the one that says increased hospital admissions, emergency room visits, and doctor's visits for respiratory diseases, because if you read the Newsminer this morning, there was an article that talked about health effects in Fairbanks and basically said that there was a measurable increase in hospital visits related to increases in levels of PM 2.5, and in particular for every 10 micrograms per cubic meter increase of 2.5 in the air, there was a 7% increase that someone under the age of 65 would visit the hospital because of stroke symptoms, 6% for people, just general for people over 65, and a 6% increase for under 65 for respiratory illnesses. So the first epidemiological data directly from Fairbanks on the issue, a fairly important data set. So at CCHRC, given that context that we have that Fairbanks is a non-attainment area because of the elevated concentration levels of PM 2.5 in the wintertime, and that we have to figure out some solutions to that problem, CCHRC has taken on a number of tasks. One is to characterize the sort of size of the residential burning problem, and also to test some appliances and to look at some of the issues around burning wood in those appliances and different sorts of wood and different sorts of appliances. And so that's what I'm going to talk about a little bit more here tonight. So we use devices called CONDARs sampling. These are 4 different samplers. We tested them in our lab. If you look carefully up high, you can see that there's 4 of them on that stack, and we're intercomparing them. One of them was actually run in a certified EPA lab in Oregon, so we tested the other 3 against that one, so we could get fairly useful results out of it. We could get the emissions using a standard protocol using the computer here. And then, so the next set of data I want to show you is from testing a wood stove. This is a non-catalytic EPA Phase 2 certified wood stove. And you see in red there, its rated emissions are in 2.6 grams per hour. That's of PM 2.5. So all these emissions are of PM 2.5. So we tested that stove with 4 different kinds of fuel: white spruce, black spruce, aspen, and birch. And then in the yellow here, those are the actual, what we measured, the emissions rates in grams per hour. So that very close, certainly consistent with what the EPA certification for that stove was. So that gives us confidence that our measuring techniques are reasonably spot on. So then one of the questions is, well, okay, if you're burning the stove essentially flat out, what if you tamp it down? What if you burn it at a lower burn rate, restrict the air? And what we found was that we get a significant increase in emissions. We go up to about 14.5 grams per hour when we're burning it at that lower rate, which a lot of people do at night. They stoke up the fires and they want to get it through to the next day. So one of the consequences of that is your stove is less efficient and you're getting a lot more emissions per hour out of that stove. So we also looked at pellet stoves, and we looked at a stove that would burn both barley and wood pellets, and we got some Delta barley and some wood pellets at this time that came from Idaho. And again, here's sort of just for comparison, here's the emission rates in grams per hour. So they're a little bit higher than that other wood stove, but the EPA limit was 7.5 grams per hour. It's going to change to 4 something here pretty soon, but these would all qualify. They'd be okay. We also looked at masonry fireplaces and did some tests on those. This is actually note masonry fireplace. So this was a project where we modified a fireplace and converted it to a masonry heater, and did the measurements on that. And it comes out a little bit higher in grams per hour, but as you'll see later, because of the BTU output and the fact that you're only running it for 4 hours a day, the grams per week or per BTU output are quite low. So this is, you have to remember that you're only running this 4 hours a day in order to get 24 hours of heat. So here's a summary then of looking at these 4 different heating devices: the EPA wood stove, the masonry heater, the multi-fuel barley stove, and the multi-fuel pellet stove. And again, in the yellow over here, this is grams per 100,000 BTU, so a comparable heat output. And you see that the masonry heater and the wood pellets are the most efficient in terms of emissions compared to the amount of heat produced. And the barley and the regular wood stove are comparable here at about 40 grams per 100,000 BTU. So then just another look at that same issue, but looking at the economics then, and making some assumptions. We just assumed these fuel costs $200 per cord, $8 per 40 pounds of barley, and $6 for 40 pounds of pellets, wood pellets. At those prices then, it costs you about $1.25 for 100K BTU, $1.06, $4.57, and $2.92. So, and of course, one of the options that's not listed on here is if you cut your own wood, you probably cut that cost to $20 a cord. And so the equivalent cost here would be 12 cents and 10 cents. So it's, you know, it's a very economic, one of the advantages of burning wood that everybody's talked about is it's a very economical source, especially if you want to gather your own cordwood. So the problem, of course, is that are these emissions, and we looked at one of the studies that CCHRC did for the borough was to look at how much those emissions are. Our calculations were that they are a very significant source. They're somewhere in the vicinity of 50% of the total amount of emissions, depending on your assumptions about how much the power plants get back in and all that sort of stuff, which is beyond the scope of our study. But clearly, I think one of the conclusions from our study was wood stove was a very significant, wood stove combustion or wood combustion was a very significant source of PM 2.5 in the borough altogether. So what are the solutions then? What are things that we can do to reduce that? So we looked at, one of the things in that study we looked at was a wood stove change-out program. Obviously the first thing we want to do is make our houses more efficient. So use less energy, use the least amount of energy that we need. That's the first thing, and that can be very significant. That can be, reasonable things that you can do to your house, you can cut your energy consumption in half for space heating. That's easy. That's the low-hanging fruit. You can go far beyond that if you want to be a lot more diligent. But clearly that's the first thing we should do. Then the next thing is that we should burn dry wood. For every increase in about 10% moisture, so if you go from 20% to 30%, there's about a 67% increase in emissions and an equivalent decrease in efficiency. Then the next thing we want to look at is more efficient devices, like things like masonry stoves and catalytic converter stoves. In every case, whatever device we have, we want to burn it hot. We want hot fires, short hot fires, but we don't want to be tamping it down or having smoldering fires because they create enormous amounts of emissions compared to what the stove does when it's running hot. And lastly, in order to deal with the issue that you need heat continuously, it's very efficacious to do heat storage. That's one of the reasons why masonry heaters work so well is because they store the heat in the rock. So we'll go through those a little bit. Drying wood isn't too complicated. If you split and stack it, cover the top of the pile, season it for approximately 6 months, you're good to go. It'll be dry enough. It'll be below 25% probably. Now, there's all kinds of variables, and we are actually doing a study right now to characterize those variables in drying wood. But since we're doing it as a contractor to a subcontractor to the state of Alaska, as a subcontractor to the borough, I can't show you the data right now, but it'll come out pretty soon. But it's not inconsistent with what I just told you. The other thing I told you that we did is a wood stove change-out, a wood stove emissions inventory. And then one of the questions, of course, that we used with that inventory was, well, suppose we did a wood stove change-out program, and converted all the non-qualifying wood stoves to qualifying wood stoves. So that's what the change-out program is intending to do. I'm just going to skip ahead here. So here's the bottom line here. From wood-burning devices generate about a little more than 1,000 tons per year of PM 2.5 at present, and that's under pretty favorable assumptions. If we simply did a wood stove changeout, we didn't do anything about hydronic heaters, just wood stove changeout, then our calculation is that we would reduce that number to 830 tons, which is about a 27% decrease. And this is based, also includes GVA power plant, Aurora power plant in the mix here. So if you took those point sources out of here, this percentage would be much larger. So we were just assuming here that those plants were contributing whatever their permitted value was. It's likely that those permitted values are much less than, I mean, the actual numbers are much less than the permitted values. So probably this number is much higher. So a change-out program can be a very significant contributor to reduction in PM 2.5 in the borough. The other thing is, I talked a little bit about the issues of running a wood stove hot, and I showed you some data about, it was about a factor of 7 increase in the emissions for a qualified wood stove if you just ran it tamped down. So another option, though, is to get a catalytic wood stove. And one of the advantages of the catalytic wood stove is that you can actually run that at a much lower rate and still get high efficiencies because of the catalyst. It's still not quite, you know, the total overnight burn, but it's getting close to it. And so that's definitely another option to consider. Masonry heaters obviously don't work for everybody, but and they're relatively expensive compared to other sources, but they have some real advantages. They're very efficient. You run a very hot fire in them, and then because of the flue path, this convoluted flue path through the masonry, the heat is stored for 24 hours. So you run a hot fire for 3 or 4 hours, and then that heater radiates heat for the rest of the day, the rest of the 24-hour period. And it's averaged, as I showed you from those week-long comparisons, averaged over a day or a week, they're very low emissions compared to any other burning source. You can also retrofit. We did an experiment to retrofit a fireplace. So here's a before picture and an after picture. This was just a conventional fireplace. It's extremely inefficient, 10% efficient. You know, all the heat's going up the chimney and these kind of things. Now here's a masonry heater, and converted this into a masonry heater, and it's very comparable to the masonry heater that's in our building in terms of its efficiencies. Another option is with the hydronic heaters. So here's a fairly large hydronic heater, and this is actually a large storage tank here. This is a 1,400-gallon storage tank that's made out of CRX or ARX blocks with a liner in it. And so again, this is a technology to try to get around the problem that whenever you size a boiler like this, you've got to size it for the coldest day of the year. And so most of the time you don't want as much heat as it'll generate, so you're running it too low, and it's smoldering and generating a lot of emissions. So a solution to that is to run it hot, run a hot fire for a period of time, store all the heat that it creates in terms of hot water in a tank like this, heat your house from the tank, and then when that temperature of the tank drops down to some critical level, fire up the stove again. And you can size these things so these are kind of daily chores. So those are a number of options to getting cleaner burning residential wood heat in your house. So I guess we'll have questions later.
Thanks, John, and appreciate you sticking around for questions here in a little bit. Next, I'd like to bring up Michael Gomes and Jesse Warwick from Chena Power to talk about the project that they've been working on out in North Pole at K&K Recycling.
Thank you, Gwen. As she mentioned, we are Chino Power, and we're here to talk to you today about our clean biomass power plant in North Pole. This is a demonstration project, and we'll talk about our partners here in a second.
My name is Jesse Warwick. I'm the engineer on staff at Chino Power. I have a degree in chemical engineering.
And I'm Michael Gomes, born and raised in Fairbanks, UAF graduate, and I do business consulting and the marketing for Chino Power. So first, I'd like to start off by thanking our project partners. Alaska Energy Authority funded our project initially, and we are working in collaboration with United Technologies Research Center. They are a research branch of United Technologies Corporation, the 20th largest manufacturer in the United States. So, oh, is that better? Okay. So tonight we're going to talk to you a little bit about biomass in general, but Gwen touched on that, so we'll go over that real briefly. Talk about specifically our Fairbanks biomass project that's at 9 Mile Richardson Highway on the way towards North Pole. We're going to talk about the power plant, the overall system that we are putting in place. Talk a little bit about organic Rankine cycle technology, and tell you where our project's at and where we're looking ahead in the future, and we'll follow it up with the question and answer section. So, as Gwen touched upon, the sources of biomass can vary. There's short rotation dedicated energy crops, or woody biomass crops, and typically those would include things such as willow or alder, switchgrass, your machanthus, but the grasses typically don't do as well in Alaska. So if we were to do a short rotation woody crop, we would probably look at willow. There's also fire line trimmings. The state has to cut fire breaks in order to keep the fire suppressed and have basically backup areas where they can stop the fire. So a few months ago, we went out with Mark Lee of DNR and looked at the possibility of procuring the biomass trimmings from that. Right now, they're just basically left there and they phytoremediate back into the ground. We're also looking at local lumber processing. Superior Pellets is also another potential source. They have a requirement that they have to have a certain type of wood, a certain composition. There'll be defects with that, and the defects, we believe that we could use those in our power plant and scrub those out. We're also looking at recycled wood, cardboard, and paper, avoided items from the landfill. Our sister company, K&K Recycling, actually just procured a deal with Fort Wainwright to get the recyclable material that could be used for this project. So some facts about biomass. It's an abundant resource in Alaska, especially here in the interior. If you look around outside, there's potential sources everywhere. In a lot of the remote villages around Alaska, it is also a viable source. If you notice, we had our Chino Power Quarterly, and on the front of that it says, do what you can with what you have where you are. So that's kind of our motto. We're looking at what the villages have. They may not have geothermal, they may not have hydro, but just about everybody in Alaska has biomass. As John and Gwen both talked about, there's carbon neutral properties depending on how you do your biomass power plant. And it's renewable and sustainable. So your fuel costs, they stay in the community. It can be a little bit more labor intensive, but again, that's local job creation. So our objectives when we set out to do this project were to make a biomass heater, a thermal energy source. That's our primary mission. Our second is to combine this technology with organic Rankine cycle technology and basically marry the two together. So as I mentioned in the beginning, this is a demonstration project, so we're looking at the viability of combining ORC technology with biomass. We're also, we planned initially for 404 kilowatt electric output. Our goal was to reduce landfill use by avoiding that paper, cardboard, and wood waste that's currently getting buried, and to increase our renewable energy portfolio in Alaska. Biomass is an up-and-coming technology, but in the United States, it's fairly mature technology that's used all over. And we also wanted to co-produce with a major utility grid to prove that it can be done safely. So our goals that we also have here are to replicate this in rural Alaska. Basically, we want to take this technology, demonstrate it, prove that it can work here on this demonstration project, and then take that to where energy costs are the highest, and that's rural Alaska, obviously. We wanted to design this power plant to be modular, something that could be skid mounted. Basically, we didn't want a lot of labor or work to have to go into setting it up. So we want something that can be designed on skids, brought up on a barge, and taken off the Yukon into a village fairly easily. We also want this biomass power plant to be able to operate on a variety of different biomass sources. Again, you have to use what you have where you are, so that may not be a big landfill or a lot of people that we have, like in Fairbanks, we're avoiding burying that stuff, but in the villages, they might not have enough paper, cardboard, and wood waste to even make this a viable option. So we also wanted to see if it would operate on short rotation woody biomass, and we're going to be expanding into that. Fireline trimmings I touched upon, and local lumber processing, and also the pellet processing. So our description of our project, it's a near 3 megawatt gross thermal energy, and that means the total energy output. That's not necessarily all energy that's harnessed, that's how much potential energy is there. Our ORCs are designed to generate 500 kilowatt electric output, and that's because they are actually very efficient permanent magnetic generator turbine technology that Jesse will touch upon later. We are planning to use some district heating. There's always the possibility to expand your district heating in the future, but again, if you expand it too much, you may lose some capacity with electrical generation. But we have set up to district heat to K&K Recycling and Chena Power's corporate office to do the district heating there. And the power plant will be carbon neutral initially, but we are planning to do some tests and studies to see how carbon sequestration may work with a co-located greenhouse setup.
So this is our project site here at 9 Mile Richardson Highway. I don't know if you've driven by, but we've done a lot of cleanup on the yard, painted the building. So the building you see here is where we're going to put the oil heater and the turbines, the ORC. Here's a little schematic of the system that we're doing. You can see on the left there's the turbines. On the right there's the heat exchangers. Those are brazed plate heat exchangers, different than what we have out at Chena. They're a lot smaller. There's pluses and minuses to it. Here's what we've built so far. So this would be the bottoming cycle of our power plant. You can see there's 3 sets of recuperators and condensers. There's 2 evaporators and 1 preheater. You can see the cold water is the blue pipe that comes in to condense. The pump down there for the refrigerant. So this, you can see it's on a skid, so this is something that we can move, quickly attach, just flange connections. I think there's 6 flange connections on this to bolt up to the hot oil, the cold water, and the topping cycle. Here's a picture of our oil heater. It's shipped on the 13th, and it should be here some point in September, and we'll start installing that. And we're going to heat oil rather than boil water for a number of reasons. One of them is so if you're in a rural application, you have problems and you have water and it's 40 below out, you're going to have some freezing problems, and this will negate that problem. And there's a lot of expensive maintenance that goes with boilers rather than oil heaters because you don't have the high pressure that you would with a boiler. Here is part of our fuel processing equipment. This is a cuber. It goes with shredder and hogger, and here's kind of our how we plan to operate 24 hours a day, 7 days a week. As far as our fuel processing, there is quite a bit of energy, so we only need to operate about 4 hours a day for the 500 kilowatt production. Our plan is to just shred and not cube the biomass, but we're going to install the cuber just in case we need to cube it. As far as safety, that's been one of our major things, and that's why one of the reasons we went with the ORC and heated oil rather than boil, because you don't have the high pressure. We'll have an overflow tank for the oil in case it does get too hot and start to expand. We'll have lots of controls, monitoring. And for the first year, we're going to have somebody on site 24 hours a day just to make sure it's safe and nothing gets, any red flags that come up, somebody's there to take care of it. And we're going to be connected to the Golden Valley grid. That's where we're going to be distributing our power. And we have to, there's obviously a lot of grid protection equipment that we'll have on site installed to keep, in case the power goes down, we'll shut down so we're not putting electricity where GVA thinks there's no electricity. As far as the emissions, working with the DEC, there's the, you can see on the left, or in the middle column, there's for construction permit with the DEC, these are the minimum values that if you're above any of these, then you have to get a construction permit. On the right is our predicted values. You can see we're well below everything. But we would be ready to clean the flue gas if needed to be, especially with the 2.5, which is starting to come around, which you've seen in this picture previously. So one of the emissions that we might have to deal with, which depending on what you're burning, you're going to have different emissions, but what we plan on burning, we don't have to deal with much. If we did have to deal with SOx, we would probably wet scrub it. It wouldn't be too hard to install anything to do that. Same with the NOx. Mostly you can just wet scrub this as well. The hydrogen, or HCl, we don't anticipate having much of this at all, so it's kind of non-issue, but it is cleanable. It's highly acidic, so a base can scrub it pretty quick. And mercury, which, as you can see from our chart, we didn't have much mercury anticipated. Oh, that's not even on there. So, but we don't anticipate much mercury, and it's something we'll obviously look out for in case we do. We'll be ready to clean it. To the ORC, this is a description of a Rankine cycle, just steam generation, heat in, evaporates the water, spins a turbine, runs the generator, then condenses, and then gets pumped back in the evaporator. Difference between the Rankine cycle and the organic Rankine cycle is just a carbon-based fluid rather than water. So same deal, you heat the refrigerant, you run the turbine, spin the generator, condense the refrigerant, goes back into the pump. We're pretty much expanding on what's been done out at China. There's been pretty good success out there with the ORC out there, so we want to continue working with UTRC, who China worked with on that, and develop this technology a little bit farther. So here is, we're going to cascade our ORC. Since we have a lot of, out at China we're running at about 160 degrees. Here we're going to have the oil at about 500 degrees. So we're going to be able to have a bigger temperature differential, which will allow us to run 2 different cycles rather than 1. So we'll have 2 different refrigerants that run at different temperatures. The higher temperature refrigerant will condense with the lower temperature refrigerant will evaporate. So we'll have 2 different cycles, and you can see we'll get 170 kilowatts from the topping and then 330 from the bottoming cycle. And our efficiency is going to be pretty high at 20%. Out at China, I think it's about 8%, from what I remember. Here's what you saw earlier was a picture of just the bottoming cycle. So here's the topping cycle next to it. You can see the piping going between the 2 where you'll evaporate one and condense the other refrigerant. Here's the high-speed direct drive turbines. This is also different than what's out at China. These, out at China, the turbines spin at a much lower velocity than what these will. And here's just, they're going to also be magnetic bearings to increase efficiency, and then you don't have to worry with oil since we're going to have a lot of high temperatures. You don't have the oils breaking down and getting in the refrigerant as well. Here's a CAD analysis that UTRC has done. You can see the strength of the housing for the turbine. Here's the CFD analysis. It shows that the turbines, or demonstrates the turbines will have a pretty high efficiency. And here's a picture of the turbines assembled that we will be using.
So our human resources are probably our key thing. Bernie Carl, as most of you know, is the president of China Power. He's dealt with a lot of projects, a lot of different grids and tie-ins he's been on and different utilities around the state. Raj Bagarva is our PE, ME, and our engineer of record on this job. And of course, we have Jesse Warwick. Bill Bilbo is also a mechanical engineer. And then we have our team from UTRC that is advising us. We meet with them on a weekly basis. And then, of course, you have myself. Some experience that we've had in the past, of course, most of you are familiar with, or if not all of you, the Chena Hot Springs geothermal power plant. We've also done various surveys and tests on the property out there and on our reservoir. Recently, we just finished a 100-year projection. And we also have completed a hydrogen field demonstration project. And we have our mobile ORC unit, which you may have seen last year at the Renewable Energy Fair, and actually it powered some electricity over at Aurora Energy, is now down in Utah making energy. So looking ahead, for the horizons, we're looking beyond Fairbanks once we prove this demonstration technology. Again, Alaska villages have the highest cost, so that's where we're looking at placing one of our first units after we prove our demonstration technology. They have access to large quantities of biomass. It can be used for combined heat and power, which would really make sense in a rural setting. And it could be co-located with greenhouses, and again, that's a future expansion of our project that we're working on. But also, not only do the rural villages have high energy costs, but they also have a high food cost. And again, it is a labor-intensive process, but that does create local jobs. This is a application map for energy portfolios from around the state of Alaska. So I'll give you a minute to look at that. The green is the biomass, the blue is hydro, and the red is wind power. Greenhouses obviously would offer a lot of benefit. This is, again, where we're heading. Food security is a growing issue, especially here in Alaska, where we import over 98% of our food. That would also help with economy, it would create more jobs. And so not only would you have technicians that would be working in the power plant, but you'd also have people that would be working in your greenhouse, and obviously there'd be a distribution chain that would be tied with that. This would help lower your overhead costs, and in the long run, if you're looking at your life and the quality of life issues with your community, it improves overall community health. So, Gwen, I guess we're done here. I don't know how we're going to do questions, so I'll turn it over to you. Thank you.
They're trying to sneak off on me here. John, if you would be willing to come on back up here for some questions. I also wanted to acknowledge a few other people in the room. Wanted to thank Representative Mike Kelly for coming this evening. Also wanted to thank Bernie Carl and his wife Connie. Bernie, of course, is the president of Chena Power and the proprietor for Chena Hot Springs. Connie's actually the owner of Chena Hot Springs, so she tries to keep him in line, as we hear pretty frequently. And also wanted to thank Jack Bear, the president and CEO of Cold Climate Housing, thank you, Research Center, for also coming and joining us this evening. So I'm hoping that we can pull the mic out of this holder. And do we have some questions from the audience for our speakers, our three speakers this evening? I actually am having a hard time seeing you guys. Okay, go ahead.
What is the working fluid, the oil that you're using for heat retention?
So the question is, what is the working fluid, the oil that you're using for heat retention? And I apologize, I'm going to be repeating the questions because we have Marcus on audio visual over there, and he needs to, we need to speak into the mic, okay?
It's just a standard heat transfer oil. Therminal is the brand of it. It's pretty widely used up north for heating needs too.
Yeah, I think the question had to do with hydronic heaters and the design of the combustion chamber, with having fire brick linings or not. And the The design makes a huge difference. With the older hydronic heaters, where there was essentially just a water jacket around the fire chamber, the fire could never get hot. It could never operate more than around 900 degrees. And so it was always essentially smoldering. And we could never get up to 1,000 or 1,500, 2,000 degree fires. And so those systems were always, maybe 100 times more, had about 100 times more emissions than the modern designs. If you look at the EPA website, there's a number of outdoor boilers that are certified for the voluntary EPA Phase 2, and they're much, much more efficient than the older systems. And the key design element is that the combustion chamber is essentially separate from the heat exchange process. So you combust the material, move the flue gas down the pipe a ways, and then do the heat exchange. And whereas the older ones tried to do that in one step, and were inherently inefficient.
I'm wondering about the percentage of plastics or paper or cardboard that you use for biomass.
We don't plan on burning any plastics, just cardboard, paper, and wood. The question was about burning what we can burn in our unit, and that is regarding plastics, cardboard, wood. Yeah, we're just going to burn wood, cardboard, and paper.
Do you know what percentage of paper and cardboard you put in?
We can handle a wide variety. That's the design of the boiler or the hot oil heater.
The question was about the recycling program. We're taking plastics. That is correct. K&K Recycling is taking plastics, but they are baling it and shipping it outside. That's not. We're not shipping any outside. Oh, correction. We are value adding in Alaska.
Thank you. We're not shipping shit out. We're losing everything here.
Standard.
Yeah, the biggest difference is in the density. So birch is a lot more dense than spruce, but on a pound for pound basis, they have a very equivalent amount of energy. So in a standard cord, there's more energy in a birch cord than a spruce cord, but on a pound for pound basis, they're equivalent. And so on a grams per energy output, you're going to put more volume of spruce through there, but you're going to get equivalent sort of emissions. Does that help you? So the question was there a significant difference between spruce and birch in terms of... Right, but you're getting, yeah, the question, and I haven't done the exact calculation for that, but when you buy a cord of birch, you're getting a heavier cord, you're getting more pounds of wood, and so it makes sense to have it be a little more expensive.
For the devotees of those catalytic burners, when are you going to test those? You're obviously in the pitch making a reference to statistics that aren't generated to compare in-house, and what's the holdup on testing those catalytic?
Funding. We actually don't have a funded project right now to look at. The question was, what's the holdup on CCHRC testing catalytic wood-burning stoves? And you're right, we haven't tested them. And the answer to that question is we didn't have a funded project to look at those yet. So we're still hoping that that'll materialize, but it hasn't yet. So it's on the drawing board, but not reality yet. But there have been a number of presentations by Blaze King at the the Hearth Barbecue and Patio Association meetings, and there's some data that Omni Test Labs generated on the efficiency of those and the emissions of catalytic converters running at the lower rates. So there is some data out there that you can get and look at.
Go ahead.
I have a question for the Gina. You're talking about making these units available for rural Alaska. Who's going to be operating those things out there?
The question is, we're planning on making our units something that can be done in rural Alaska, and who would be running them out there? Well, the goal is to have the residents in the rural areas operate them. That's one of the reasons we're not going with the steam. We're trying to make this something that can be done with not a whole lot of training. I mean, obviously there's going to need to be training, but this is something that we're trying to make simple that can be done in rural Alaska.
But have you considered the cultural aspects of that? The reason I bring it up is because I have experience on the North Slope where a fancy plant was put in, and the problem was that when whaling season came around, the operators would go out and do the whaling and stop maintaining the unit. And there's a lot of that, in the interior as well. All these groups have these cycles, seasonal cycles of operation, hunting and fishing, etc. And it's sometimes difficult to find somebody who's going to commit themselves to get in the role of maintenance of some kind of a device. So I just wonder if you've looked into that at all and considered it.
Okay, so the comment was essentially paraphrasing that in rural Alaska you have to worry about schedules and people with their cycles, hunting, whaling, fishing. There's not a whole lot we can answer for that. I mean, in the end, if they want to live in rural Alaska, they're going to need energy, and they're not going to be able to sustain themselves off of what they're paying now. And it's just a sacrifice they're going to have to make. If they're serious about it, they'll have to do it. If not, they won't.
Yeah, what's the cost of your units? What's your anticipation of maintenance on them?
The question was, what are the costs of our units and what's the maintenance? That's a number that we're not all that comfortable putting out right now because we're still in the process of developing it. There's obviously going to be some shortcuts we can do once we put this unit together. Maintenance, it's somewhat of an unknown right now just because it is a pilot project.
What temperature will the contents burn at?
As far as, the question was what temperature will the biomass burn at? The exact temperature I'm not sure, but it'll burn hot, it'll burn clean. We're going to heat the oil up to about 550 degrees when we're running with the topping cycle.
I ask because I feel that plastics will still be involved, no matter how hard you try. And chlorine, paper that has chlorine on it, and then I think about dioxins. Have you considered dioxins?
Okay, the comment was the integrity of what we're burning. A little worry about there being contaminants in there, and that's something we're going to be cognizant about, is having a high integrity fuel source. And we're planning on burning a lot of wood, which is a clean product. As far as everything else, we'll have a watchful eye out, and we'll burn clean fuel.
At one point, there was a chart up that showed the cost per 100,000 BTU and different wood types. The cost, what was it? For birch, the cost per spruce to get 100,000 BTU. Could you put that in perspective and compare that to the cost of fuel oil?
Yeah, the question was, could I compare the economics of burning the wood that I showed to the economics of burning oil? And I did have another slide that had those comparisons, but unfortunately I deleted it from this PowerPoint presentation. But it really depends upon what you assume the costs of things are. And kind of if I remember correctly, the crossover point is approximately $250 a cord and about $2.50 a gallon for fuel oil. So there's, they're equivalent BTUs at about that. So it depends on how much you're paying for a cord of wood and what the price of oil is. And there have been times recently when the cost of a purchased cord is actually more expensive than fuel oil, but normally it's the other way around. The normal condition is that it's somewhat cheaper to buy cordwood than it is to burn fuel oil. And certainly, of course, if you're cutting your own, it's way cheaper. But if you, my email address is john@cchrc.org. So if you want to shoot me an email, I can give you a copy of that other graphic. Yeah, the assumption was that all of the non-certified stoves, and I don't remember the exact numbers, but somewhere around 3,000 stoves get converted over to qualifying stoves. So basically we sort of distributed them over the range, but we used the 7.5 grams per hour as the top limit, so that we assumed that all the wood stoves that were burning in the borough after the change out were 7.5 grams or less. And it was that conversion from having, it's approximately half of the stoves being non-qualified to all of them being qualified that gets you that 27% reduction.
So if people keep burning like they are, a lot of green wood's being burned, that has really no impact on that 27%?
The question was, if people keep burning as they are and burning a lot of green wood, does that have any impact on that 27%? Excuse me. I'm not sure I quite understand the question, but the assumption we made in estimating the PM 2.5 emissions from residential combustion was that everybody was burning dry wood. So the fact that people aren't burning dry wood means that we have an even higher upside. So if we can both do the change out and convert to drier wood, we can make an even larger percentage change. And also, I pointed out that we had to assume at that time that a significant fraction of the fixed point sources, that is the power plant, PM 2.5 was actually in the airshed too. If you take that out, then the percentage climbs also. So that's a low estimate of the effect of the change out program. The question was, do we know how much the effect of people who are burning coal and the people who are burning green is going to be? And the problem is I don't have any data on the percentage of people that are burning green. We did a very preliminary survey of people's wood piles and went out and we did 50 wood piles around, sort of randomly selected around the borough, and measured the moisture content of those wood piles. And actually, we were somewhat surprised that probably 50% of the 50 were 25% or less, in that range. So that the problem of green burning may not be quite as large as we thought it was. And I suspect, although I don't have any data to prove this, but I suspect that the biggest problem with green wood is with the outdoor wood boilers, because they just need so much more wood and it's harder to acquire it and dry it and deal with it. So, and in those calculations that I showed you, I didn't consider outdoor wood boilers at all. I just left them out of the equation and just looked at wood stoves. And then the question about coal is, on a per unit basis is a very dirty burner, but there are very few of them. We use the numbers from a study that ACEP did in terms of the total amount of coal that was being sold for residential burning, and it's really quite, it's almost negligible in the large picture in the airshed. It's not negligible, however, of course, if one of these is next door to you. Sure.
The gentleman who asked about the price per BTU.
Right.
That's very dependent on whether you get wet wood or dry wood. If you get wet burn, the BTUs go up the chimney just to boil off the water.
Yeah, that's true, but if, you know, I prefer myself to buy green birch and dry it. I find it more cost effective that way because I can get the cord for cheaper, and you know, Mother Nature will dry it for me if I just let it sit there for 6 or 12 months. So, but you're absolutely right. I mean, it's really crucial to not be burning wet wood for two reasons. One is the efficiencies go down. You're going to burn maybe twice as much wood for the same heat output because you have to spend all that heat to drive off the moisture. And also you're going to be creating a lot more emissions for the same amount of heat output. So the point of not burning wet wood is well taken.
Another question from the
John, I understand there's a ballot a measure on the municipal ballot in Vermont that would relate to policies that regulate some of the home heating practices you outlined. I'm wondering if you have investigated that ballot measure and if you know where people might go for more information.
Well, I think one of the sponsors is right over here. So the question was about, there's a ballot measure that relates to, I think you're talking about the one that relates to prohibiting the borough from restricting the combustion using wood stoves. And if that is the question, then talk to Tammy Wilson over here. She's one of the co-sponsors of that. I haven't researched it particularly, other than my own personal opinion is that I think it's a bad idea. I think that the citizens voted for local control and we ought to proceed with that. That's my personal opinion.
Question, aren't there other burning devices not available in the United States that are clean and work well because they're not EPA approved? They will not get credit even if they have something manufactured locally?
No, I don't know the answer to that. There are scrubber technologies that are available in Europe that are relatively expensive. They're not, we've tried to acquire those, that is get, you know, prototypes or test modules, but most of the companies that are manufacturing those aren't interested in the North American market at this point in time, so it's been very difficult to do that. But the other problem, as Gwen pointed out in her study, in her comments, was that the efficiencies of combusting biomass go down with the size. And so since this, at residential scales, it's generally not cost effective to spend a lot of money on scrubbers or bag houses or cyclonic cleaners or electrostatic precipitators. And also, because of the scale and the difficulties in controlling the burn rates, things like electrostatic precipitators tend to clog up pretty fast. And when we consulted with Omni Test Labs, which is one of the major test labs there just out of Portland, Oregon, they basically said that they were not aware of any scrubbing technology that was economically feasible to work at the scale of a residential wood stove. So it's kind of, we're still looking for that, but at this point in time, we haven't found anything that looks promising, especially in this market. Question over here.
What kind of metering and test equipment do you have to verify your emission projections on your biomass burner, and what kind of reporting will you be doing on
We were using a Condor sampler. Oh, the question is what kind of test equipment do we do for the emissions sampling? Oh, so this is for you guys. Okay, sorry.
The question is, where we got our numbers for emissions and how we're going to monitor it. We got our numbers from the oil heater manufacturer and the monitoring of it. The DEC, I'm sure, will follow up on us on that. I mean, we'll work closely with them. That's a little bit down the line, but we'll monitor it, obviously. That question is, are there any requirements that the DEC has? And that is actually something that's somewhat in flux right now. They're passing some, they're pushing, just went for comment period where every, I don't remember the specifics of every wood burning application that's not residential would have to have an annual test of where they come in and sample your flue and figure out what it is. And that's actually a big problem with rural Alaska because that's an expensive test, and for some of these Garn oil heaters, that'd break their project there.
When are you expecting your project to come online? And when do you expect the greenhouses to come online and be in production?
The question is when we plan on producing power and then when we plan on having the greenhouses up and running. We're planning to start producing power in November of this year, and then the greenhouses we'll probably install a couple acres next summer.
I'm trying to figure out how the biomass is getting to your plant. Do you have a fleet of trucks, or are you expecting people to bring it? You're going to tip them? Is the government involved in bringing it there? How's that work?
The question is, how are we getting our biomass to our facility? And the answer is, we are presently we're planning on shipping it ourselves with trucks, and we don't have like a large fleet of trucks. We have, several trucks that are going to be bringing the biomass to us from Fort Wainwright, and we're also in talks with a few other organizations around the borough to see if we can procure more biomass. So the answer is, right now, yes, we do have trucks, and we are getting it ourselves with no subsidies.
About 5 years ago, I heard a talk from Alaska Village Initiative about the Biomass system. It's a mature gasification technology used for about 20 years in Asia. And they were touted as being able to feed the gas directly into diesel generators so you don't have to have expensive modifications. They were looking to evaluate it for rural Alaska. I was just curious if you heard of any follow-through on some of those evaluations.
Yeah, the CCHRC was involved in the initial looking at those things, and we went quite a ways down the road with trying to get a contract with Biomass to bring a prototype unit up here. It turned out, however, that the farther we got into it, the less economic it looked. And in talking, doing some due diligence and talking to some other people that had been trying to operate these systems, we found out that they were spending more than the $1 million purchase price on engineering consultants to get the thing up and running in the first place. And so we backed out of that deal. And right now, we don't, we're still interested in seeing if the system works. It works in theory, but as Gwen pointed out, the question is how much money are you willing to spend in order to get the thing to work? And right now, our opinion is that it's not worth it. And I can expand on that and say that in spite of a 2-year effort, we have not found any small scale, that means 500 kW or so, CHP gasification system that appears ready for, that you click and add to cart, that's ready for the market. 5,000 watts, 5 kW, yeah.
For Jesse, your slide about the emissions seemed to indicate that, and your comments toward that DEC's regulatory requirements? And if that's the case, I mean, are you getting a permit, or you don't think you're gonna need a permit, you're not gonna get a permit?
The question was about permitting for a project with regards to the DEC numbers that are shown on the slide here. According to the 18 AAC 50, we are not required to get a construction permit for this project if we are under those numbers.
And you said that, in terms of the plans at this point for the platted sign mile, that you're expecting that it'll be under, so you're gonna go ahead and start burning in November, and you're not gonna worry about the permit.
The question is that since we're under, we're going to go ahead and burn and not worry about permitting. I mean, we're in close contact with DEC. We've talked with them today. I mean, we are being diligent about this, and so we're not going to surprise them with anything. But no, we don't need a construction permit. But I mean, we are working close with the DEC because where we're located is kind of one of the more important areas as far as emissions.
Just a couple more questions. Any more out there?
Right there.
Are you guys gonna consider, this is for Chena Power, consider doing a voluntary source test, just sort of for the research aspects?
The question is if we're going to consider doing a voluntary source test to gain knowledge, and that's something we are looking into, getting instrumentation to monitor what we're outputting, so we have data to back up what we're doing, and it just helps promote what we're doing if we can show what we are doing.
One more question? Go ahead.
On your generation, are you looking to go online with the grid for baseline demand or handle basically peak demand?
The question is if we plan, I don't really know how to phrase it, if we plan on going to baseline demand or peak demand. We plan on producing 500 kilowatts 24 hours, so I guess baseline would probably be the answer.
I wanted to thank the Alaska Center for Energy and Power staff that have been helping put this on. Marcus Mager, who's doing the audio-visual, Elizabeth Usabelli, who's been running the table there and has done a lot of the prep work leading up to the series, as well as Amanda Bird and Jack Schmidt that are here. Yeah, no problem. And thank Representative Wilson for coming here, as well as the Borough Assembly members and all of you. Thank you for coming and joining us. If you have additional questions, hopefully our speakers will stick around for a few more minutes and could answer a few more. And John, you want to say a few words?
I just want to say that in the box back there on the table are copies of my PowerPoint presentation if you want to get that.
I brought Chena Power quarterlies, although we don't have enough, so please help save the environment. Electronic copies are on chenapower.com.
Okay, thanks to all of you for coming. And again, if you have ideas for future topics that you're interested in, please fill out our survey. We would really like to hear from you.